Thanks very much, Andrea. And an AI assistant is taking information down for this meeting as well. Thanks very much.
Okay, perfect. Okay, so just continuing, DHI is now a global presence with very different offices around the world, and with reference to South Africa and all the South African region, EcoSource is our long-lasting partner and agent for those all activities related to software. DHI is a full independent company. Is a private organization, but is a not-for-profit organization with a strong focus on research and innovation, meaning that we don't have shareholders who in the end of the year share what are the profits, but profits are typically reinvested in research and innovation activities. Our areas of expertise focus on water 360 degrees, so it's not just marine environment that we're going to talk about today, but also surface water, groundwater, and all related to water distribution, water collection, and treatment plants. And of course, all the other industries that are related to water, like oil and gas, aquaculture, agriculture, climate change, and so on. DHI main activities are working on projects. We have around 2,400 around the world, but of course we are well known also for our mic software that we're going to talk about today. Marine, we are working in different type of activities, supporting design, supporting impact assessments in different typologies of investments like marine infrastructure or related to dredging, climate adaptation, reclamation, all the environmental activities, and of course also ports and terminal. DHI is well known for our mic powered by DHI modeling suite, which is the state-of-the-art modeling package for all physical and water quality, environmental and biogeochemical processes related to water in all the different water environments that we just mentioned. So we could say that for each of the different phases of the water cycle, starting from reservoirs to river, to groundwater, to the sea, coast and offshore, there is always a DHI module and model that allow the simulation of the specific physics and process. Together with the models, DHI developed and maintain a lot of additional technologies like all the decision support system technologies addressing port management, but also treatment plant, sewage, offshore wind farm, and so on. That's because in the recent year, the traditional numerical models that are of course continue to be used in what they call the offline mode to support design and analysis are more and more getting used also as engine of real-time decision support system, and this is also what I'm going to talk about today. Also, there is a lot of please mute the microphone who just joined. Thank you. And so sorry, I can hear someone talking. Can you please kindly mute the microphone, please? Thanks. And just to complement, there is a lot of additional data portals that allowed and speed up the preparation of the numerical models and the simulation by accessing larger databases of hindcast data about waves, currents, bathymetries, and so on. So I will now give you an overview of mic models in the first part of my presentation, and then I'm going to give you some examples of projects around the world where the numerical models have been used. So DHI started 60 years ago from physical modeling, and right now there are still a lot of very important basins for physical modeling in our headquarters in Denmark. But numerical modeling has been the main focus in the many years, starting to develop the first numerical engine since the 70s, and then being progressively updated and maintained. These software are used in our advisory projects and also made available to all consultants, researchers, and private and organizations that are using those all over the world in their project. So of course the mic modules followed all the journey in the IT technologies in the last in the last decades, and has been always maintained and to the level being the state of the art till today, state of the art until today. We are going to talk primarily about Mic 21 and Mic 3. The name Mike of the Mic modeling suite comes from Mike Abbott, who was the one who developed the first numerical solver for Mic 11, who was the first numerical model developed by DHI. So you will see Mike in the name of all most of our software. The number that follow represent the dimensions where the equation are solved. So Mic 3 is a fully 3D module. Mic 21 is a 2D model, which is solving the equation in both the horizontal, the two direction of the horizontal space, but is averaged on the vertical direction. There is also Mic 12, which is used in specific cases on riverine, where you have to differentiate on the depth, but you can average in the space and in the horizontal dimension. And Mic 11 is a totally 1D model with the averaged equation both in the horizontal and vertical space. These modules allow to represent the physics, the hydrodynamics, but also all the related processes like waves, like sediment transport and the ecological processes and so on. So all the modules are strictly interconnected. Typically, hydrodynamics is the main module, the heart, but all the other processes are directly linked and with the mutual interaction. As said, the mic modules are now, we could define them state of the art because they integrate the most advanced scientific know-how with the progressive developments on the IT side. So turning and being accurate, very usable, and allowing your productivity, but at the same time maintaining the top level from the scientific on the scientific side. All modules are now based on the flexible mesh approach, meaning that we are using unstructured meshes that allow to increase the resolution in those areas having that requires a higher detail. This is the Lagoon of Venice that I'm going to talk about today, and you can use a lower resolution in the area offshore that you have to include in your model, but that are less important. On the vertical, there is also the option to use both the Z level and the sigma level. Modules, just a quick overview. The first one is the preprocessor, which is basically the graphical interface and the tool that allow the preparation of the simulation and a lot of and the output. Mic 21 SW is the spectral wave module. This one is used for simulating, is the first type of module that allow the simulation of waves, representing is a phase average module that allow representing the wave propagation and the wave transformation. This is the most commonly used module for waves, but we can also go further in terms of complexity on the simulation. These are specifically cases representing cyclones and spectral analysis on your left, again done with SW. But there are a lot of additional modules that are available in the Mic by DHI modeling suite. Mic 21 Wave FM is the new version of what was called previously the Businesque model. So it had one more layer of complexity, allowing also the simulation of diffraction and reflection, typically used within ports and harbor. And now, starting from the 2025 release, this is also based on the flexible mesh approach while the previous business model was based on a Cartesian regular grid. So this is the top new product that has been just released by DHI in this 2025 release. These allow also at the first level also the simulation of the wave run-up and consequent flooding on coastal area, but it's typically used for closed basins, and it includes all the diffraction and reflection that I just mentioned. Still increasing further the complexity, the Mach 3 wave is the top of the gamma model for wave propagation. Is a fully 3D that is of course a phase average, phase resolving, and allow high resolution simulation also of run-up and coastal flooding. And this is the product that was released in 2024 and is the highest complexity but also the highest accuracy product that we have in the DHI modeling suite for the simulation of all the wave related phenomena. And this is what is normally used typically for coastal flooding as you can see in the animation running now. Then moving away from the wave, as I mentioned, the hydrodynamic module is typically the heart of every simulation, and it allows the representation of currents and water levels both in 2D and 3D depending on what is the need for your specific project, and of course can use in input the output of a wave simulation. Of course, there is also the opportunity to have the two modules running in an integrated way, so you have a feedback of waves on the currents and a feedback of currents and water levels on the waves. On top of the hydrodynamic module, it's possible to implement water quality and transport modules. The first one is now on the screen is the advection dispersion module. This is the simplest one, just solving the advection dispersion equation with the possibility to include also some simple transformation and decay of the solutes in the water, and this is normally used for simulation of a non-reactive pollutant as for running a simulation of water or flushing within closed basin as a preliminary assessment of marinas and so on. That the first one is a Eulerian module. There is also a version, a Lagrangian module like the particle tracking that again simulates the propagation of particles based on the results of an hydrodynamic simulation, but using a fully Lagrangian approach. As you can see, it's based on particle simulation and not just of a concentration within the water column. Then again, adding complexity, we can mention Ecolab. Ecolab is a full package for the simulation of all water quality processes in water, again based on top of the hydrodynamic simulation, that where you can include all the equations representing water quality processes, meaning eutrophication, meaning any reaction.
Andrea, you've gone on mute for some reason. Please unmute yourself. Andrea, can you hear me? You've gone on mute.
Yes. Can you hear me now? Yeah.
Yes, we can hear you now.
Perfect. Someone muted me. Maybe my speech was not that interesting. And let's continue. So as I was saying, Ecolab allowed the simulation of all the water quality processes, including eutrophication, reaction, heavy metals processes, and so on. And then also there is the possibility from the recent version to simulate also what we call agent-based modeling, which means that we can also include the behavior of the substances or any other of element which is included in our simulation. This is an example of larvae dispersion in an area in Singapore, where you can also include the behavior of the specific particle. It could be also an animal, or that move differently in the water column depending on the temperature, on the water quality, or could be any other type of element that is moved around in your domain, where you can also include the reaction to the physical and water quality variables within your model. Oil spill is another module that is very that is used a lot in the recent year, that allows the simulation of the propagation of any type of pollutant related to oil or gas. CO2 also we are simulating recently on some projects, and includes also the processes in terms of transformation, evaporation, and decay of the substances related to oil, of course requiring a specific equation to represent the different processes that characterize the spill. You can see some example now on the video running. For example, you can see different components of spill from a blow up with different processes happening as in this case. Then we have a lot of modules for coastal processes. LeadPack is the simplest one, representing simulating on a 1D approach the coastal processes, the coastal sediment transport, and the evolution of the coastline on a 1D approach. This is the most commonly used tool for coastal studies, but also we have a fully 2D simulation with the sediment transport module for non-cohesive sand that can be used also in a morphological approach with time-varying bathymetry, as you can see in this specific case related to the siltation of a harbor in an area just behind the breakwater. Typically, ST is used receiving an input, both the waves coming from SW and the hydrodynamics coming from the HD module. And then again, increasing also complexity, there is a shoreline module, SM, that allow also the evolution of the coastal profile on a long-term simulation, still with a 1D module, but also allowing the morphological processes, which is needed because you cannot really run a fully 2D morphological model addressing 10 or 20 year evolution. You can do in 1D, or you can do with this type of compromise, which is the shoreline module merging 1D and 2D approach. This is just another case with evolution of a coastal process. Then we have MT, that is used, the mud transport, that is used for simulation of cohesive or mixed sand and mud, that is normally used for dredging and evaluating the impact of any dredging plume, normally within environmental impact assessment processes. And then we have additional modules for mooring analysis that is commonly used for design and verification of a harbor for all the mooring lines. And this module allow also taking into account all the response of the ships moored, taking into account wind, taking into account waves and currents, as you can see in the animation. And it also allowed the very nice simulation of a passing vessel, and as you can see in this case, the influence of a passing vessel on the moored or on another vessel that is moored, that starts moving following the waves created by the passing vessel. On top of all the modules that I briefly presented to you, there are a lot of additional tools that can allow and empower your productivity, like data extraction, data conversion, time series management, and all the tools to interact with the publicly available databases of data like Copernicus and so on. There are a lot of ways to access the mic licenses. I'm available for those of you who would require more details, and also Jason and Nicholas Source are your contact point in this case for the South African clients. Basically, it's available in subscription or perpetual license, and there are also specific licenses for the academy research institution as a full usage online. Typically, subscriptions are packages that allow to purchase or to rent from minimum 2 months up to 1 year or even further the specific modules that you need for specific projects. And I'm not going to talk about prices now, but you can just see on the screen which is the order of magnitude of the cost for per month, which is normally affordable within a specific project. That means that that's why the subscription is the solution, is the approach that has been growing a lot in the recent year, because normally, I'm just referring to consultant and private industry in this case, you can just rent the module for the period you need for the execution of your project within your project budget. Of course, DHI provide a lot of support in using the modules from the basic standard support that is included in the licenses, in the license agreement, and all manuals and training that are available also online. We offer training and support even on the job, helping you in the execution of your project. I would leave probably to the end the questions, so I will move to the second part of my presentation, giving you some very high-level overview of projects. And the two presentations that will follow will focus on specific projects more in detail in South Africa, but the intention of this presentation here is just to give you, on one side, some more international flavor, on the other side, to showcase the different typologies of projects that are normally conducted using by DHI softwares. So as I'm Italian, I'm going to give you some example from Italy, but also in other countries in my region. This is a quite famous system that is fully operational, running real time for supporting the operation at the Mose movable gates that has been built in Italy to protect the Venice Lagoon and to avoid the flooding in Venice. You can see on the picture how it works, typically when there is a high surge in the Adriatic Sea. And all this system is based on Mic by DHI modules, simulating the surge and forecasting the surge from the Mediterranean Sea up to the Adriatic and in the lagoon, and all the influence of the gates. You can see a recent event that was in 2022. One of the many where the Mose system has been used with all the forecasts and the effect of the Mose that when it's closed allow avoiding the flooding in the lagoon. So all this is based on a very complex modeling chain, which also use ensemble forecasting with different meteorological models that run in parallel, and then waves and hydrodynamics model that I just mentioned, forecasting the levels in the lagoon. On top of this, we as a DHI in Italy, we offer 24/7 service to the control room, which is in Venice, supporting the operation of the Mose gates. The same system has also being used for the design and the verification of the gates of the Mose. As you can imagine, it's a very complex system of these gates that are totally submerged and raised in case of high water levels. So again, the mic models has been used with that purpose. You can see microwaves, spectral waves, and all the others that I just mentioned. Still in the lagoon, the same modules has been used also for the analysis of how to optimize the navigation of the Malamocco Marghera channel, which is basically the channel that is mainly used for all the ships entering the Venice lagoon and being and reaching the Marghera harbor, which is up here. So this is the channel, while Venice is here, and used now also for the cruise. For the cruises arriving to Venice. There has been a lot of discussion in the past about the big cruise ship passing near the San Marco Square and the Venice area. And now that this also based on this project, the approach has changed. And within this project, the mic modules has been used together also with all related to the anchors, so the moving ships processes to simulate the impact of the displacement wakes of the ship passing in the channel and creating these long waves that creates erosion processes in the Venice lagoon that, as you can imagine, is a very critical area. So specific measures, also full mission simulation has been run together with the numerical model. We did the specific measurements campaign also to calibrate the drawdown effect, which is the reduction in water level that you can experience when a big ship is passing in a channel, and simulating all these processes of erosion and stress on the bed, addressing some mitigation measures that are both infrastructural, like creating additional salt marshes and mud flats as in this area, but also operational, meaning reducing the speed of the ship, of course, on one side ensuring the safety of all the maneuvering of the ship, on the other side reducing the impact on the Venice lagoon. Moving to a totally different type of project, mic modules are largely used on a lot of analysis supporting impact assessment in oil and gas industry. Most of these projects are confidential. I can just give you a very high overview of what are these type of studies. These slides refer to a typically production water discharge in the sea, production water coming from any type of processes like LNG, typical LNG, or also the extraction of oil and gas from the subsea. And within the environmental impact assessment process, it is normally required to run a specific simulation that goes from the metocean characterization of the area, that of course is needed also for the design and support of the operation, down to simulating the dispersion of the effluent, both in the near field and far field, and also running all the additional environmental analysis down to the risk assessment with the different substances that are normally released in an oil and gas process, and evaluating the impact on the ecosystem and the biodiversity. The same can be applied to other type of releases. This is a case in Africa regarding to methanol spill with all the related processes coming from another large extraction process in the say northwestern area of Africa. And in this case, also the oil spill module has been used to simulate the specific processes that relate to the methanol dispersion. Again, addressing the risk analysis and the impact assessment on the ecosystem. Recently, also CO2 dispersion studies are largely required. That's because there are a lot of projects around the world about carbon capture and storage, typically in exhausted extraction area, that were initially used for extracting oil and gas, and now they are going to be used for storing CO2 in the seabed, and there is there is a large need of modeling supporting the impact assessment of potential spill and dispersion of CO2 that normally affects the pH of the water with the potential consequent impact on the ecosystem. So in this case, specific equation has been implemented in Ecolab. Ecolab allow you also to write your own equation related to the specific substance that you are going to simulate. Of course, this has been also calibrated and so on. So it's a quite new typology of study related to the CO2 in this case. A lot of other dispersion projects can include thermal effluents, as it normally happens for the analysis of the impact of a cooling system of a thermal power plant, a nuclear power plant, and so on. This is another case in Israel. In this case, there is a large storage tank that is used for flood prevention, and the scope of this project was again to evaluate the impact of the release of this fresh water after the storm coming and the related impact on the biodiversity and on the reef in the Israel area, where the approach is again the same, starting from large scale, in this case the full Mediterranean, because some processes can affect the Israeli coast, starting from specific long swell waves coming from not all the Mediterranean but half of the Mediterranean, and down to the specific process of dispersion near the coast. Offshore wind farm is also an important large market where the usage of numerical model is now a standard. There is a lot ongoing in Italy, in France, in other countries where I am involved. And numerical models are used on one side for the metocean characterization of the area. That's of course used for the design basis, both for traditional offshore wind farm as for floating ones, specifically for the Mediterranean in this case on the screen, but also for many other areas around the world. DHI developed high resolution hindcast models, typically for waves. Some are also for currents, that has been largely calibrated. Also satellite data on top of buoys were available, and these data are normally used for this type of analysis. For wind farms, what is typically studied with models together with the metocean analysis, including also joint probabilities and high complexity and metocean analysis. Typically, a wind farm can create an impact, a shadow effect on waves. So this is not what is normally asked by the Environmental Protection Agency as a part of the impact assessment procedure. And here you can see some example where the SW spectral wave module has been used, representing in the model mesh and bathymeters the presence of the farm, as you can see here, very high resolution, and the impact and the shadow effect on the waves in this case. But also cyclones, many cases, again talking about the Mediterranean, in this case, are normally to be simulated, and this is now possible with specific tool within Mike. Tsunami risk is also something that is normally addressed in this type of analysis. And more recently, we are now including as a standard also climate change potential impact on this type of analysis. Normally, when you do a metocean study, you rely on hindcast data, assuming that what happened in the last 40 years will be the same climate for the coming 40 years, which is probably not such a correct assumption. There is a lot of uncertainty about climate change, but So what we normally do is using these large data sets that are now made available from larger search center like those in Canada or in Australia in this case, and perform the same ocean analysis under different scenarios in terms of emissions, but also under different models that are used by this larger search center to evaluate what is the potential impact in terms of uncertainty on the traditional metocean or extreme value analysis. And as you can see, there are typically some models that are saying that the waves will increase, other models will say are saying that the waves will decrease. So what we will get in the end is a sort of uncertainty analysis that can be used as an uncertainty factor or safety factor in the design.
There's 5 minutes left on your presentation.
Yeah, thanks.
Thank you.
Thanks. Other projects related to offshore wind farm address what is the sediment dispersion during dredging. That's also what is normally used for all the cables connecting the offshore wind farm to the land. Other projects moving into the port are studying what is happening within a specific harbor in terms of waves. Again, in terms of dredging, this is a case of Port of Genoa, where there is a specific analysis of the downtime and wave agitation in the different at the different area. Another project is addressing, in this case, the impact of the vessels moving in the very narrow channel and the related impact on the moored vessel in other location. In this case, using the mooring analysis tool that I introduced, which allows simulating all the movements that a moored vessel is can suffer both from wind, from waves, or a passing vessel, as I mentioned. Other studies relate the support to the sustainable coastal developments, and we are running a lot of projects. I'm quite sure the presentation of PRDW coming later will also address this topic, so I will go rapidly. These are different cases around the world where the numerical model has been used for simulating waves, hydrodynamics, sediment transport, and also wave run-up and coastal flooding, supporting the design of protection scheme in both in small villages, small areas as the ones that we are seeing here, or in larger development. This is another project related to the construction of the potential construction of the bridge connecting Sicily to the mainland of Italy, where again all coastal studies has been performed, evaluating the impact on the bridge on sediment transport, coastal erosion, and so on, in a very complex area of this narrow channel between Italy and Sicily, where there is a strong interaction of waves, tide, and current. Moving to large projects, we are very much involved in different locations in Africa. This one is addressing Egypt, where a lot of developments are ongoing, and typically in this case we use numerical model to address and guide sustainable development of the area, typically suggesting defense schemes that are working with based on the working with nature approach rather than working against nature. So typically we tend to prioritize natural-based solution rather than gray solution in terms of growing breakwaters and so on. And we typically follow the study from the very early stage in terms of feasibility, including all the coastal flooding, inland flooding, down to suggesting what are potential protection scheme for the protection of the coast, with very innovative solutions as the ones that you can see now on the picture, and these are other cases in this specific project. Typically this project in Egypt include also a lagoon, a coastal lagoon in the area, where we typically perform all the analysis also in terms of water quality and flushing in the area. This is another very important project that is very well known in the north of Egypt, where both the lagoon studies and the coastal studies has been performed by DHI as consultant using the numerical models. Last few minutes about the real-time systems. I already talked about the Venice Mose. I started there, but I just want to complement this with additional real-time system. This is again on Gino. I already talked about that, where we have a real-time wave forecasting system that allows forecasting the waves approaching the harbor and entering the harbor, so that you can identify in each specific location which are the forecasted wave, and based on that optimize the mooring line or what is the planning of the operation within the harbor. This is another case of a port suffering large siltation, and in this case the system is forecasting the sediment transport and the progressive sedimentation in an area that is just upstream the harbor that has been dredged. So it's a sort of a sediment trap, and we can monitor and also forecast what will be the progressive filling of this sediment trap and plan the dredging in advance in order to avoid the port to be siltated and the operation stopped with additional increased cost. Other system is addressing water bathing water quality, as this one that I'm showing in the Ligurian region, where Genova is, where I'm now sitting, and this one is addressing is simulating the impact of the different effluents, both from treatment plants but also from rivers in the area, that allow to forecast the water quality and eventually start some specific alarms in case there is a pollution in the sea that can prevent the safe bathing of the bathers in the area. Last slide is about ENCOS, which is a new product that has been released since a few years by DHI that allow the safe transit of vessels in navigation channel, the safe mooring, and also the optimal planning of all the port-related activities. So ENCOS includes a lot of different modules, mainly addressing the harbor masters and the shipping industry. And I should spend a lot of time presenting you ENCOS. This is just a quick overview of the different modules, and this is something that would require a more specific presentation, but again is just to prove in the end how more and more the numerical models are used as an engine of real-time systems, as I mentioned. That was my last slide. Sorry, I had to run because there was quite a lot I wanted to present to you in this time, but at the same time we didn't want to give you a too long presentation. I'm of course available for question and for any further contact in case you wanted to have more specific insights of some of the projects that I presented or the mic modules. That's it from my side. Jason, back to you.
Fantastic. Thank you, Andrea. That was a fairly comprehensive overview of everything. I'm sure that some people are a bit overwhelmed by some of the information that's been presented, but thank you very much. That's brilliant. We've got 10 minutes or so for questions. Andrea kept to his time pretty well. So if there's any questions, please raise your hand, and I'd like to. All right. Nelson, please go ahead. If you don't mind introducing yourself, that'd be great.
Good morning. My name is Nelson from Transnet National Ports Authority. I'm an environmentalist by profession. Thanks, Andre. I think it's just too much information. I hope we would have that presentation and slides just to go through it on our own. I never heard you saying anything about possible modeling the propagation of underwater noise. You
Yeah.
do those kind of studies within your tool kit. Thanks.
Thank you. Andrea, I don't know whether you
Yeah.
want to answer that.
Yeah, sure. It's just again just a matter of time. I didn't mention that in the mic modeling suite there is also one module I didn't include, which the name is UAS, underwater acoustic simulation, that exactly allow the propagation of noise within a water body, taking into account the physical variables, typically density coming from temperature, salinity is one of the main parameters, but of course all the representation of the bathymetry and the water column is important. And UAS allow the simulation of the impact of noise and the propagation of noise, both from a point source or a moving source. Point source typically is used for perforation analysis or dredging at a specific location. Movable source is used normally for or moving dredger or typically passing vessel that can create noise. And you can simulate the propagation of the noise wave in the water column, which is normally used for impact assessment processes, because you can then match the maps of noise that you get with the maps of animals that are normally in that area, so you can quantify the impact. And you can also couple the noise module with the what I mentioned ABM module, agent based, so that if you know how a dolphin will react to a specific frequency of noise, you can implement this equation in the ABM module and typically run simulation that on one side will show the normal behavior and movement of the dolphin in a specific area with and without the noise source, generating what is called density map of the specific species, and therefore really quantify what can be the impact of specific activities, activity in creating noise in the water column.
Fantastic. Stephen, you've got a question?
Yeah, thanks. Yeah, Stephen Luger from PLDW. Andrea, you showed an example of using modeling CO2 with Ecolab. Have you done anything similar with ammonia?
Yes.
Now with green ammonia being increasingly popular.
Correct. Yes, we did also studies like including ammonia and quite a lot of other typical, let's say, pollutant or effluent, typically in the oil and gas industry market. I can confirm that. And as you can imagine, most of these projects are confidential, so it's not possible to mention the name and the client, but you can imagine the context, as I'm sure you are also involved in this type of project.
Lesiba, let's move on to you. Thank you very much for that answer, Andrea.
Okay, thank you, Jason. Thank you for a detailed presentation with various areas of application. So I just wanted to check with regard to the simulation. Is it based on what data? Is it space-based, like satellites, or is in situ, or is based on radar instruments? Just to check.
Yeah, sure. Typically, radar data, satellite data are used in the calibration or validation of a specific model, typically waves, but also currents. So typically data that are used are, we could say, different typologies. Can be in situ data. Normally consider that the bathymetry is the one you will always need, and that can come from a specific survey, or nautical charts if we are offshore, or if you need lower resolution, or satellite derived bathymetry. Now is quite a standard in quite clear water and clean water up to -10. the bathymetries that are directly derived by the satellite are now quite standard, specifically in those areas where surveys are not available. In terms of waves, we normally rely on own or publicly available databases of hindcast, so reconstruction of waves along decades in the past. Of course, buoys data or current measurement instruments allow to calibrate and validate locally. For all related to spill and pollutants, typically this is the data that you get from the developer or from let's say your client, and you can again include these in the model and use local measurements for calibration. Radar is now starting to be used, specific radar that can detect the wave field in specific area, and we are running some specific project really to calibrate is both direction, the wave model on the radar fields, but also vice versa, because it's not that straightforward to define the wave field from what you get from the radar. So it's also this type of dual help that the radar and models are giving each other within this specific project.
Thanks, Andrea. So I'm just going to go to the comments very quickly before I go to Zanoxalo related to that. So Annalie had a question, which I've sort of answered. I'm thinking of water lettuce issues that we've had in the Vaal River in the past years. Can Mike software also be used to model the spread of macrophytes such as hyacinths and water lettuce on the surface of waters in rivers and dams? And my answer to that is yes, it can be done. You would have to set up a specific Ecolab template for that and run that either on a 1D, 2D, or 3D modeling application. Andrea, have you got any comments on that? Sorry, have we frozen here, or can?
No, I think Andrea's frozen.
Is Andrea frozen? Okay. Andrea, you seem to be frozen. I don't know whether you can exit and enter again. All right. Zanoxalo, do you want to ask your question in the meantime, and we'll move on to, well, we'll try and answer it internally. I don't know whether we will be able to.
Okay. My name is Anopolo Palmer from Transnet National Port Authority. I'm a GIS specialist here. Colleagues, I just want to ask you mentioned at the beginning that the Mic 21 is developed by DHI, and it is a commercial software. But you also mentioned that you are a non-profit or you are non-profit making organization. I just wanted to find out if maybe do you have a trial version or demo, because I saw that you said, like, in terms of the licenses, you have academics and so forth. Do you have some demos or demo version or trial version for people that are eager, like, to learn this Mic 21? If there is a demo or a trial version, what are the limitations? What can you perform? Because I know that some numerical models, like if it's a trial version or if it's a demo, then you are restricted in terms of the size of the module and the duration of your simulation, stuff like that. That's the first question. Then the second question is that you also mentioned that a bathymetry is something that you must have it every time, like when you are performing these models. What do you do in cases where, because currently at in our ports in our port system, we perform our hydrographic surveys around the ports, like near shore. On inside the harbor, for instance, right? But the parts that are a little bit far away, then we don't have data set for that. I know that the publicly available data set like GAPCO or naval charts can be quite dispersed or coarse. So how do you determine then the accuracy of the model if you don't have like a detailed bathymetry uh, far from the harbor? So those are my few questions. Thanks, colleagues.
All right, thanks, Zanok. So, yeah, so I think I'll answer the first question. I'm going to hand it over to both Andrea and probably Stephen Luger to answer your second questions on the bathymetry side of things. In terms of the first question, there are trial versions of the software available. We also give you a limited time sort of usage of the software if you're wanting to try something out. It's also important to note that we have MOUs with 5 universities across South Africa. So it's the University of KwaZulu-Natal, University of Benda, University of Stellenbosch, University of Cape Town, and University of Free State. And 2 of those are quite heavily involved with the Mike sort of 21 applications and modelings in Mike 3. And those would be Stellenbosch and University of KwaZulu-Natal, and occasionally UCT does some stuff related to that. And then students, there are, if you're motivating and doing a master's or something like that, or a PhD, there you can use the software, and you would get those licenses basically given to you for free for the period of your particular modeling. But any commercial applications, etc., there is a trial period, and then after that you would need to either purchase or not purchase the model. Yeah. I hope that answers your question. And yeah, it's also important to notice that there are different models related to that. So you can buy subscriptions. So if you're looking at something related to a limited term project and stuff like that, it's quite easy to run. Now, I'm running a little bit into Stephen's time, but I'm going to let Andrea or Stephen Luger answer that bathymetry question for you. Thanks.
Yeah, I can take it rapidly. I would say normally, of course, the more you go offshore, the less accuracy you need in bathymetry. And normally nautical charts or specific database that are also made available by DHI normally allow you to have the resolution that to reach the resolution you need for specific project, typically for pre-feasibility or initial assessment. There is a specific module in Mike Suite, which is a CMAP that allowed the handling, the access to large databases of bathymetries and also handling of these. Of course, there are specific projects if you are targeting an extraction project of oil and gas or something similar, you will always need a specific survey of the area. Near to the coast, as I mentioned, the satellite-derived bathymetry is also a concrete option now that provide a good accuracy. That's the answer in short. And of course, if you have some specific project in mind or a specific area, we can check together separately what we have eventually available that we can provide. I don't know if Stephen want to add anything to my answer. Otherwise, I think it's time for him to start the presentation. Yeah.
Well, just to lead in, yeah. So I mean, often we have to commission a bathymetric survey as part of the modeling study, if there is a lack of data, and that would be one of the first tasks would be to do a bathymetric survey.
Excellent, thanks. Stephen, well, while you're online, I'm going to move straight on to you. So Stephen is director at PRDW and one of the South African expert users, I'd say, on the software applications. So I'm going to hand over to you to introduce yourself and take us away. Thanks, Stephen. I'll also give you some extra time just to make up for the 5 minutes that we have now.
Okay, thanks, Jason. Is it about 15 minutes?
Yes, that's correct, yeah.
Okay, good morning, everyone. I'm Stephen Luger. At PRDW, from PRDW Consulting Port and Coastal Engineers in Cape Town. We have a coastal modeling team of 10 people at PRDW, and we've been using Mike for about 20 years now. So this morning I want to talk about this study, which is modeling coastal flooding in a changing climate at Small Bay, Cape Town, using Mach 3 wave. I want to acknowledge my colleague Stuart Walker, who did the modeling in the study, and also the City of Cape Town, who were our client. So just to show you the project location, this is the City of Cape Town over here, and Table Bay, and across on the northeast here is, zooming in, is Big Bay and Small Bay, and then on the southern part is Small Bay, and the study area is really this piece of coastline shown in red. And this is what it looks like on a calm day, and this is what it looks like on a less calm day. So the objective of this project was to design and construct a robust seawall to protect the infrastructure against flooding and damage from the sea. So we looked at overtopping rates and flooding and the design waves and water levels to calculate the forces on the new seawall. And the coastal modeling tasks were wave refraction modeling and wave overtopping modeling. We also had to do water level analysis and sediment transport, but I don't have time to discuss those today. So the wave refraction modeling was done with the Mach 21 spectral waves model. It's a flexible mesh model. We used a fully spectral instationary formulation. So the model includes local wind wave generation, nonlinear wave-wave interaction, and then dissipation due to white capping, bottom friction, braking. It also has refraction and shoaling, and the effect of a time-varying water level. Model, it's a spectral wave model, and it doesn't explicitly model diffraction. So the reason we need to do this is the model domain here, and this is showing the June 2017 storm. So we have about 11-meter significant wave height offshore, and we obtain the offshore data from global hindcast models. We have fully spectral data that we can apply in the offshore boundary, and then the refraction model is used, if we look at the detail here, is to actually refract the waves into the site. So the site there is Small Bay, and we have a location in 13 meters of water depth just offshore of the site. And you can see that's and by that stage, the waves have reduced from 11 meters to 5 meters due to refraction and friction. It's this particular site in this westerly condition. You can see it's sheltered by Robben Island. So we have refraction around north and south of Robben Island. We have calibrated the model. So we basically pretty much calibrate all the models before we use them. We had data at a site in 30 meters water depth, quite close by, and we had 3.9 years of data, hourly data. So horizontal axis is the measured significant wave height, and the vertical axis is the modeled wave height. And we're looking for a 1-to-1 relationship. We always expect some scatter because some of the scatter would be uncertainties in the hindcast boundary condition, and just there's always some variation. But if we look at the QQ plot, which is the purple line, you see it's almost 1-to-1, which is what we're looking for. So what we did then with that model is to simulate 357 storms over this 40-year period or 42-year period, and extract the wave height at that point 1 in 13 meters of water. And this is over time. You can see this is the extreme value series. It's interesting to note that the biggest 2 storms were in the last 5 years of this time series. But this is not a talk on climate change, so I'm not going to go into discuss that anymore right now. But I can just say in the last few years we haven't had any more of these big storms. So that's doesn't seem to be an ongoing trend. We then use this extreme value series to do an extreme value analysis shown on the left here. We're putting a Weibull-3 distribution, and you can then read off, for instance, the 100-year wave, upper 95% confidence limit would be about 6 meters. So that would be the output of the spectral wave model, and we can associate a period and a direction and a directional spreading to that as well, also from the spectral wave model results. So then we move on to the overtopping model. So here we're using the Mach 3 wave model. It's a phase resolving model based on the 3D Navier-Stokes equations. So it now really includes all the physical processes that you really get with nearshore waves. So it'd be wave refraction, diffraction, friction, surf and swash zone, hydrodynamics, breaking and run up, overtopping, flooding, and even wave transmission and reflection through porous structures. The limitations, as Andrea said, was its higher computational cost compared to the spectral wave model, and also it's not like a full VOF model, but it's a lot faster than a VOF model, so it can't handle an absolutely vertical wall. The steepness of your structure is limited by the grid size, so you can't model you can model an almost vertical wall, but not a vertical wall, or definitely not an overhanging or a recurved wall. But there are ways around that limitation. So this is a simulation now. So the boundary condition here, the offshore boundary condition is 13 meters. So it's the waves that we got from the spectral wave model. But now we're running a fully phase resolving model. You can see the wave crests, or the light lines, the light colors. This is surface elevation, and the troughs are the dark colors. So you can see we have a fairly long crested sea state coming in towards Small Bay and Big Bay, and you can see all the processes. You can see refraction, you can see diffraction here behind the island where this tombola or salient is. And if you look carefully, you can see the flooding and reflection of the coastline. So this is there's not really any processes that are left out in a simulation like this. So when Mach 3 wave first came out, I think it was probably 5 years ago, before we started using it commercially, we did our own validation of the model, and that we did a number of different run-up and overtopping tests. This one is the closest to the current situation. It's a flume test from Goda, and you can see it's a vertical wall with a 1 in 10 foreshore. And this is the snapshot of the model, cross-section down the flume, and you can see the water surface elevation, and you can see the orbital velocities below the water surface. And we're interested in overtopping. So if we monitor the discharge across the crest of the structure here, this is over a period of 15 minutes. The red lines are showing the individual overtopping events in meters cubed per second per meter of crest length. And the blue line is showing on the left axis is showing the accumulated volume of overtopping. And in this plot here, if we compare the measured overtopping rate to the modeled overtopping rate, again, we're getting that 1-to-1 relationship that we're looking for. Overtopping values have a very wide range, orders of magnitude different, so we always use a log scale in this case. We didn't have any measured data at the site, but we did a more of a qualitative validation of the model at the Small Bay site. We had this photograph. We knew the exact date that the photograph was taken, so we simulated that exact date and time in the model, in the spectral wave model, and the Mach 3 3D, and we then looked at the model results, and we plotted the time series of the inundation for the sea state at these 3 points, which we could also identify in the photograph. And for instance, looking at this wall here, you can see how the water has come about 0.5 meter up that wall. And this is the time series at that location, and it's broadly in agreement. So that is a qualitative calibration of the model, site-specific. If we look at components of coastal flooding, we have the tide and sea level rise if we're looking at the future. And then we have storm surge. That's the increase in water level due to onshore wind or low atmospheric pressure. And it varies in the order of hours. And then superimposed on that, we have wind waves, and they cause wave setup and wave run up. This plot here is showing the offshore wave height and the storm surge at Cape Town over for about 40 years. So the wave height is the offshore hindcast wave height, and the storm surge is the measured nearshore storm surge calculated as the measured tide gauge level in the Port of Cape Town, so minus the predicted tide. And the first thing to see about this diagram is that in Cape Town, the waves go up to about 11 meters offshore, and the storm surge the nearshore storm surge only goes up to about 1 meter. So looking at this diagram, you can see that the wind waves and the wave run-up is going to be significantly higher than the storm surge component. But in other places where you have tropical cyclones and wide, narrow, shallow coastal shelves, and certain geometries, the storm surge component could be significantly higher than the wind wave component. And in that case, you could probably just use a two-dimensional hydrodynamic model to model storm surge. But that's not the case here, so we need to do the full 3D phase resolving wind wave modeling. The other thing we're looking at here is the correlation between the wave height and the storm surge. Do we get big waves at the same time as we get storm surge? In general, you can see it's pretty much a bit of a shotgun, but there is some indication up here in this quadrant that some of the bigger waves are associated with some of the bigger storm surges. And we do have a way to quantify this correlation. But in this study, we used a little bit of a more simple approach, and we said that they are moderately correlated, and we therefore combine a 100-year wave with a 10-year water level and vice versa. So always a factor 10 different. So for instance, here, if we look at a joint return period of 100, we're going to use a 10-year wave and a 100-year water level, or we use a 100-year water wave and a 10-year water level. And the waves would be from the extreme value analysis. You can see the wave height there, and the water level there would be the tide plus sea level rise plus the storm surge for that return period. So these are the different cases that we modeled in the Wave 3D model. And this is a simulation now zooming in on the site itself. This is a simulation in 2024 of a 5-year return period event. And on the left is showing the surface elevation. So you can see the waves coming in and overtopping the land. And on this side, we're just showing the inundation depth just behind the wall. We just filtered out, we've edited out the water depths offshore because they get they're very big because the seabed is low there, is deep. We're just focusing on what's happening behind on the road and around the houses, and we also can look at the current speed. And this is a situation where they've just raised the road level, but they haven't actually built a seawall. And then there's a simulation here where they've actually now added the seawall. We've added the seawall into the model, and we can see what the effect of that is. But again, you can see even for a 5-year return period, there's still significant flooding. And this is now just a cross section along that line there. We're showing a cross section. The top is just with the road level slightly raised compared to the original level. And here's the road level plus this 1 meter high seawall. And again, looking just at the profile view, so you can see the waves coming and then overtopping, and you can also see the orbital velocities shown in the colors below the surface.
We've got 2 minutes left.
Great, thanks. And then this is just to emphasize that the left is the water depth behind the wall, and the right-hand side is the current speed. And if we flick to the effect of the wall, you can see that that's the effect of raising the seawall. Reduces the extent of the flooding. It does not stop it. You'd have to make the seawall a lot higher, which has other implications around ponding of the water behind the seawall, loss of views. So the call was just to put in this 1 meter high seawall. You can also classify the overtopping depending on these sort of rates of overtopping that you could find in Eurotop, whether it poses a hazard to pedestrians or vehicles or actual damage. And just to see that you can quantify these in the model. So if you look at these overtopping rates, it's pretty much raising the wall by 1 meter reduces the overtopping by a factor of 4. And also takes you out of this danger zone here where you're going to get actual damage to the road. The other thing we had to do was look at the impact of the waves on the forces of the waves on to design the seawall and the anchoring system to the seawall. So this is a time series of the water surface in front of the wall, and we can do a time domains analysis on that and extract things like the the maximum wave height, and also the maximum water depth at the structure, which would be the still water level at the structure, which would include wave setup and the actual seabed at the toe of the structure. So this is that photograph in 2018, how it used to look like, and this is actually a photograph I took last weekend, and they're about 80% complete. So you can see they've raised the road level, they've strengthened up the whole seawall, and they've added this 1 meter high coping with 1 meter high wall on top. It has a return wall on top. It also has gaps to let the water flow out. As you saw, there is still going to be overtopping. And then to conclude, we've validated this wave 3D quantitatively against the flume measurements and qualitatively against those photographs, and it can simulate all the relevant wave processes. And this is quite a complex site, and we think it provides significantly more detail and more useful results. A traditional approach would be an SW model to get the waves at the toe of the structure, and then the Eurotop empirical overtopping model to estimate overtopping. For instance, what we get out of this, we can look at individual overtopping, we can look at maximum overtopping, we can look at mean overtopping, we can track the flood depth and the velocities behind the seawall. We can route that flood water and test draining options. And we also get those time domain wave statistics, such as H max. Limitations is that high computational cost, and the steepness, as I mentioned before, is limited by grid size, and we cannot resolve like this recurve on the wall, but we are looking at a workaround for that. For instance, Eurotop uses reduction factors to account for a recurve, and it would be possible to do something similar in the wave 3D post-processing of the wave 3D results. So thanks very much. I don't know if we have any questions now, Jason, or at the end.
Can we push those to the end, I think, Stephen, but thank you very much for that presentation. Looked very cool, and yeah, I must say it's good to see some good engineering using some stuff, and sensible engineering as well, not trying to make a structure that is just too big to manage stuff. And certainly those velocities and impacts look like they were reduced by that your wall implementation there. All right, let's move on to Christian Milan also from PRDW, giving us another example. Go for it, Christian. I'll let you introduce yourself.
Great. Thanks, Jason. Good morning, everyone. I'll just quickly share screen, get my presentation up. Yeah, so good morning. I'm Tiaan Milan, also part of PRDW in the numerical modeling team, but with the past recent, probably about 6 years, been focusing more on vessel motion modeling and how to modeling the coupling between the Mike Mooring analysis model with the Mike Pusanescu wave model. I think, yeah, just to mention that Andrea did mention the new Mike 21 wave FM model, which is an upgrade to the Pusanescu model, as well as the Mike 3 wave model can also be used for what I'm going to present now. It is a bit more computationally expensive, but all these models rely on the Business wave equations to get the wave processes coupled into the dynamic mooring analysis using MA. So maybe just the first question is why do a dynamic mooring analysis? Yeah, it can be used in all stages of engineering, from concept stage to test if some concept is feasible, all the way to detailed stage, yeah, assisting the structural design of say a piled jetty. But just some key highlights is we can calculate berth availability, see how efficient your berth in the port is. We can validate the mooring design. That's to check all the key furniture, fenders, ropes, bollards. We can calculate mooring loads, as mentioned, for structural design. Test survival conditions, if it's a port of refuge, if it's successful, if a vessel can stay safely during a storm, or even determine under what environmental conditions the vessel can stay at berth. Optimize the harbor port design, assist the port planning of a harbor, for instance, how long a breakwater needs to be to provide sufficient sheltering to a moored vessel, and to quantify the motion envelope to specify what loading equipment to be used on a quay, or even offshore application where a vessel is connected to a floating, or a subsea hose connected to a plim, how big of a motion envelope that moored vessel will have. But first, a mooring analysis is only as accurate as what you feed it. And mostly waves are the governing factor. So that's why we use the wave models. Specifically, we're looking at the Business wave model, and we're using Saldanha Saldanha Bay as an example here. I also mentioned during the previous presentations is that these wave models model all the wave processes accurately and captures all processes. So just looking at the short wave left-hand plot from the model boundary, there's the spreading both in direction and in frequency. We see some nice diffraction around the breakwater going into the port. There's wave refraction in the Greater Bay, wave shoaling in the shallower areas, and then also wave breaking and partial reflection of wave energy off the beaches. What's normally not seen, but what is underneath that is the long wave energy. So on the right-hand plot, it's the same model output. We just filtered out the short wave energy. And for the purposes of this presentation, short waves are referred to as swell waves between 5 and 25 seconds, and long waves from 25 to anything to 300 seconds. So there we can just see the bound long waves coming into the bay that's still bound to the swell waves. And as soon as they reach and reflect off the coastline, they get released as free long waves and interact with the incoming waves as well. Why is this important? Especially as time goes on, vessels gets larger, and larger vessels respond to longer period waves, and especially if resonance gets built up. So the graphic below, you can just see a large vessel in shorter waves will respond less to a large vessel moored in a long wave climate. Just another example, lots of you will recognize this. This is the port of Kuga. Starting at the right hand, the port of Kuga providing very good shelter against short period waves, again up until periods of 25 to 30 seconds. The breakwater really doing its job with a very a big gradient of sheltering there at the entrance. But looking at the long waves, when the short waves are filtered out, we can still see significant long wave energy getting into the port, and that animation just shows it in time. And as soon as those waves get into the port, they get reflected off all the surfaces and just bounce around. And harbor resonance can also be generated, especially there in the rectangular basin. You can see a standing node right next to the quay. And if a large vessel is moored on that node, that's the area where most resonance will be built up as you get the largest hydraulic gradient. So long waves are important. It's like mentioned, for larger waves, but it's also the harbor resonance, the wave reflections. All of those coastal processes or wave processes have an effect on your moored vessel. And that's the beauty of the MIC suite, is that all those processes can get integrated into the MIC MA model and be accounted for in your mooring analysis. That graphic there, you can just, at an instance of time, see how the waves change along the length and the width of the vessel. And then the time series below, it's also show the effect of long waves and harbor resonance. The blue on the left-hand side is just surge motion of the vessel, and the right-hand side is line forces of your spring lines. The blue showing just if short waves are accounted for, and the red is if you add in the long waves. And you can just see you can get up to more than a 10-fold increase in motion and accompanied line forces. So it's very important to capture that. And like I said, the MA model can consider the full wave flux field. That is the direct output of the Buzinesque wave model, and it gets applied over the full hull of the vessel to accurately model long wave forcings and other processes as well, such as diffraction, refraction, and reflection, and most importantly, harbor resonance. But for offshore applications, you can get away with just a point wave load, but as soon as you're in a harbor, there's a lot of processes that can be governing and is mostly governing in a study. Just looking at what you can do or applications to prevent those or to mitigate any wave forcings. Maybe firstly is it depends on the problem that you're solving or trying to solve with your wave model. You can do a ship-to-ship transfer, two vessels next to each other with a multi-body model. You can model MBMs, given that it's a fairly stiff MBM mooring, but it has offshore applications. But most conventionally, it would be a fixed berth, either a jetty or a fixed key structure. And in the model, we set it up in obviously geographical space, giving reaction and deflection properties of fenders and your lines. You get different types of fenders. There's just a bottom left example of a supercone fender that accounts for buckling of a fender. Next to it is just the relative difference of different line materials. You can have a soft mooring or a fairly stiff mooring, depending on what lines typically gets carried by vessels and what commodity typically gets carried by vessels. And if harbor resonance or long wave actions pose a problem, it can be mitigated by changing key furniture or adjusting line pretensions, making it mooring more stiff or more elastic. And as soon, if you're still experiencing problems, you can introduce smart mooring systems. And DHI have partnered with Trelleborg and built in the capabilities of the smart mooring equipment into the model itself. So that would be the auto moor, which is essentially a kind of a fender system with vacuum pads sucking against the vessel hull and dampening motions dynamically in real time. And there's also the dynamo, which is essentially a moving bollard, which can stem tension or release tension on a mooring line actively, again, on the go. Those systems doesn't only increase operability of your facility, but also adds another level of safety, as they are active load monitoring systems, but also active dampening systems, and has proven to significantly dampen and improve your port operability. So that's nice that they partnered with Trelleborg, and then we can directly use those capabilities within the model. So as soon as you set up your environment,
We've got 2 minutes to go. Hey?
Okay, great. I'll go to the second to last slide. This is just a process to show where how berth availability, just a few steps that we need to run through. We set, if you set up your vessel mooring is in the time domain analysis, we feed it mid-ocean combinations depending on the level of study. But we can, this is just an example of the yellow nodes, it's discrete cases that we model to encompass the full envelope of expected operational conditions. So in this case, there was 5 parameters: wave height, wave period, wave direction, wind speed, wind direction, and we can also account for currents. And we run these cases, and then the engineering relies in the feedback loop, where we look at any optimizations that we can do to the mooring, and we rerun it and until we get an optimized mooring layout. And then we process all the results. In this case, there was 1,404 cases, and we interpolate the results of each case onto a hindcast time series of environmental data with the multilinear interpolation tool. And that gives us a time series of vessel motions and line forces and fender forces that we can use in the uptime assessment, which looks like this. So with the time series of vessel motions or forces, we can do statistics such as exceedance curves or just normal time series. But we normally compare it against limiting criteria, either site-specific, like a shiploader envelope, or international guidelines such as PIANC or OCIMF. And we can get in calendar space periods of when the berth is operational, when operations need to be halted, or periods where the vessel actually needs to leave the berth due to exceedance of the capacity of the mooring equipment. And we can do, we plot that on a calendar basis, so we can see any seasonality and any connection between the vessel response and the environmental condition. So for this case, we can see in the winter time in the southern hemisphere, it's you can expect more downtime compared to summer. So that's mostly maybe frontal wave systems or something that can happen. More to the southern west coast of Africa. And that's me. Thanks, Jason.
Fantastic. Thanks, Christian. That's brilliant. It looks like a exciting application, and assuming that it's relevant, particularly for Transnet, etc., in terms of those berth mooring availabilities and stuff like that. Well, I'm going to give you a very, very short presentation on on some different sort of application or something different to what we had, and then we'll go into Q&A sessions after this. Please, if somebody can just confirm that you can see my screen. Can you see my screen? Anybody?
Yeah,
Yes,
yes,
we
can.
can.
Okay, thanks. All right. I'm just going to take you through something a little bit different with some examples and some stuff that's really kind of hot off the press. So we're going to take you through. So I'm going to discuss limnology modeling with some South African examples. I'm told that I should always give you an agenda, so you've got a very short agenda. I'll discuss some applications of Mach 21 and Mach 3 in South Africa. These are mainly terrestrial applications. I'm a hydrologist, not a marine sort of specialist, so a lot of it has got related to that, but there are some estuary example, or there's one estuary example. So we'll discuss some flood modeling applications, some water quality modeling, and some agent-based modeling. So from a flood management, risk management perspective, thought I'd just show you this. This is a simulation that we did on the lower Mkomati. So the lower Mkomati is below the Crocodile River as it goes out to Nelspruit. And somebody was asking about using information to verify these data sets. So what you see over here is actually satellite images of a flood wave that came through. And then we ran a simulation that equated to that. And in actual fact, the correlations are not too bad. Some of it you don't see because there's inundation in some of the sugar fields, but it's still shielded by cane. But that's the inundations and timings related to that, which we could then confirm against the model. The measured data is point data, which is also calibrated against, but it doesn't give you the full spatial sort of example related to that. This over here was quite a large model. It's I think it's the largest, well, at that stage was the largest flood model that was run in the Southern Hemisphere. And it took several weeks to run. So when we're talking about computationally expensive, that's the computational expense. The type of things that you can do related to this is you can map different land uses out, and then you can actually work out what their vulnerabilities associated with these different land uses are, and you can chart out different hazard ratings. So with the 2D flood modeling, what you get, Mach 21 is a 2D model. You get the velocities, inundation, and you also get duration of sort of events and stuff like that. So with that type of information, you can do a lot more explicit flood modeling than you normally would with just a 1D model, for instance, and then from that you can actually get vulnerabilities assessments associated with that. And what you see over here on the right is priorities associated with different protection measures that needed to be put in place to protect against a 1 in 10 year base flood. And then we can run through different scenarios and see how we can resolve that. And in this particular case, actually, one of the main resolutions associated with that was actually putting a flood barrage in one of the rivers up at the top near the road over here, which actually enabled a whole lot of this flooding to be mitigated on the sections coming through near the Tongaat mill over here. So that's just an application related to that. Other applications are in surface terrestrial sort of applications, having a look at exposure related to rainfall runoff on can be mine sites, urban areas, and these types of things. Again, Mach 21 is used there because you're wanting to get both velocities and durations and depths, not just depth as one of the elements. Okay. Now, a lot of you have been asking about water quality modeling. So at the moment, what we're doing is we're actually having a look, and I'll give you some live examples of this, of eutrophication modeling in different dams on the Umgani system. Some of them we're modeling in 2D, and some of them we're modeling in 3D. Well, one of them we're modeling in 3D, which is the Nanda Dam. What we've also done related to this is we've captured different information related to satellite imagery, and we're able to show eutrophication patterns in these different reservoirs from Sentinel-2 imagery with the various manipulations related to that. So this is verification information that we'd use to verify and validate the models. And then what you've got over here, or correlate, correlate the models as well. Suspended solids. So there's a number of these factors that we look at that have correlated from the satellite imagery that we can then use to track the water sort of quality in these reservoirs, and then use that to run these models. This is a Nanda Dam, just to show you the sort of process. I don't know why it's doing that. Show you the process of sorry, I'm just going to stop that for a second. Show you the process of setting these up. So here you've got a situation where you develop a mesh. These meshes are unstructured meshes, so they're triangular meshes that are set up. This is a 3D model that we're running on the Nanda setup. Once you've got the mesh, you then need the dam bathymetry, and these can be difficult to obtain. In general, they should be available from the designs and the surveys, but they're not always there. So there's, you've got your bathymetry sort of setups, and then you've got in this particular case, we've integrated Ecolab, which you see over here. So Ecolab, we've got the hydrodynamic model set up related to these simulations, and then you've got a whole lot of equations. In this one, we've used a template. There's a specific template that's run associated with that, and the Ecolab simulations using this eutrophication template with certain of the processes that we've dumbed down or switched off because we just don't have some of the information related to that. So a lot of the sediment processes and the benthic vegetation is suppressed in the particular model that we are using related to this. And I'll just give you an example of this. This is kind of hot off the press. So this is the simulation, and what we've seen over here is the computational time that's taken. I actually stopped the run about a third of the way through, and that was already on 110 hours of simulation. I was hoping to finalize the simulation for you before this. This is just a eutrophication result that you can see over here. This is the model that's going to run, and I'm looking at, in this particular case, the phytoplankton setups, and it's looking at the carbon content in the phytoplankton setup. There's a whole lot of other information that we can have a look at in this modeling application. I'm not going to take you through that. I'll just play that for you now. And what you see over here is I'm looking at a specific event where there's actually quite a large influx of nutrient and sediment, etc., that comes in from these main river reaches on the either side of the system, and you can see the propagation of the algae plume coming through related to this into the actual system itself. So you'll see how it goes, and there's some temperature elements that actually accelerate the algae growth once the nutrient has sort of come into this area, and you'll see those responses happening quite quickly now. And this happens reasonably fast in the actual dam itself when we see this propagation coming through. And the idea associated with this is the draw off associated with waters at this area over here, and that can be impacted by these algae plumes that come through the dam. And then for a verification of this, if we're having a look at those types of things, we can go onto actual satellite imagery related to that. So I've taken out the same sort of dates. Sorry, so this over here is the propagation. So that's the start of this period that you've seen, and what you can see is there's the sort of propagation of that algae going through. Sometimes we don't pick up everything because it's cloud cover in these areas, and then that propagation sort of moving a little bit more physically through. Let me just try and capture that for you properly. So we would expect this to be sort of replicated, and we can chart the actual patterns related to that, as well as getting the information set out related to these things. And then what's important associated with these setups over here is that the hydraulics is quite well computed. So I'll just show you very quickly. Oops, I need a different layer for this. So here you've got Albert Falls Dam, and you're getting a large influx of water coming from the main tributaries and a couple of the smaller tributaries over here. And you can see how this event that's coming through with the high flows propagates into the dam. And then obviously this information that we've got over here will influence the mixings and the ratios associated with things, which can allow you to model that water quality components. All right, so let me go back to another element that I would like to show you. And that's the last bit is some agent-based modeling related to these setups over here. So let's just play this for you. So what we had a look at over here was just a little bit of an experiment looking at the Knysna seahorses and seeing if we could model those. We didn't get this particular project, but we did do some simulations, particularly on jellyfish in terms of agents in the area. That is not a Knysna seahorse, by the way. I couldn't find an image of one when I was looking for the presentation. So you've got a much more funky looking seahorse than a Knysna seahorse. But what you've got over here and what you see is this over here is the Knysna Heads. So they're the Knysna Heads over here, and this is the Knysna Lagoon, sort of estuary sort of areas. And what we've got is a whole lot of jellyfish coming with a certain weight pattern, etc., into this area. And here you can see those agents moving through the Knysna Lagoon system. And some of them will get stuck in some of the places in the sort of estuary, etc. And those would act as certain foodstuffs and nutrients for potential different species in those areas. So just giving you an example of some of the use of this related to tidal sort of fluxes in the Knysna area. And I hope that gives you a slightly different application of the models. I mean, most of it was covered by Andrea, but at least some South African examples related to that. So thank you very much. I know that was quite quick, and yeah, let's move on to questions if you've got any. Thank you. Yes, Annelie.
Oh, thank you, Jason. That was really very interesting. I'm sorry, I'm Annelies Swanepoel. I'm principal scientist in the labs at Rand Water, and I also specialize in algae and phytoplankton. So I'm really interested in the phytoplankton models that you've been running. And I just wanted to know, do you only use satellite data, or do you also add lab-generated data to run these models?
Yeah, sorry, I kind of missed that, but yes, there's a whole lot of information that we get from the LIMS, so the Laboratory Information Management Systems at Umgani Water. And we generally use those, particularly on your input channels to run the sort of nutrient loadings, etc., that we're getting into the system. That they do need to be sort of, yeah, I mean, certain the measurements, etc., are quite difficult and yeah, I mean, unfortunately, with water quality sampling, a lot of them are taken with sort of instantaneous measurements at certain times, so you can miss various elements. But what we use those for is to kind of check and calibrate against the setup. So we've actually calibrated the satellite information against the LIMS data. So in running the satellite-based information, and there's more variables than I showed you there that we have a look at. We take that information, we take I think it's 9 cells around the particular measurement point, and then we'll take the average sort of feedbacks that we get from the satellite, the different sort of spectral models that we use, and then we correlate those with water quality. And then the reason that we use the satellite is that with the measured data, you're obviously measuring at a point, and we need with these types of models to get some verification of the spatial distributions and to see that we are doing that relatively accurately. So that's why we use it. So it's a combination of laboratory information, actual measured water quality, and the satellite data. Okay. Right. I hope that answers your question. Okay, perfect. Thank you. Right, are there any other questions related to that? And we've got 3 presentations that you're asking questions for. It's not just mine, but Stephen's and Christian as well. And Andrea, if you've got some other questions for him. All right, I've got a question for Stephen, I think, is with the application of things that we've seen at the moment. I mean, you've used that these Bosonesque sort of wave models, etc., to do engineering design. Are you seeing more and more of the application of modeling in these types of analyses, or is it something that's done infrequently?
No, I mean, for us, it keeps 10 people busy. So it is part of pretty much a standard part of the design, or it could be done at a pre-feasibility level. It could be done at environmental impact level, and then right through to a detailed design level. And yeah, the sort of the whole aim of it is the more accurately we can model, the more we can optimize structures. So if you're not sure of your result, you need a 1.5 kilometer breakwater. But if you have a very accurate model and you're confident of your results, you could maybe reduce that by a few hundred meters and save a lot of costs in the actual construction. So that's where they really can be helpful.
Yeah. Excellent. Yeah. I think that's also the principle, is rather model it and not experience it, which save a lot of costs. So that's brilliant. Are you also seeing more and more sort of requirements and applications towards the real-time stuff? I guess I'm asking that of you and maybe Andrea as well, where people are more sort of keen on seeing these marine forecasts. Something we are seeing in a lot of the stuff that we're doing, as we are moving more and more to real-time applications where we set up models to run scenarios on a real-time basis. And I don't know whether that's happening the same in the marine space.
Yeah, it should be. The application Andreas showed with the bathing water quality, for instance, there definitely is a need for that. But we haven't done something like that yet. There are applications for like short-term during like construction of a pipeline or something. So short-term operations to predict metocean conditions during construction period. Definitely. But the operational port systems is definitely the need for it. We haven't done a lot of that ourselves yet. I mean, TNPA do have the iPort system that they are using.
All right, excellent. And then that take up of the mooring analysis stuff, Kristen, are you seeing a lot of that usage across South Africa and maybe other African sort of port applications? And I mean, it looks to me like it's something that could potentially save clients quite a lot of heartache and income in that, money in that circumstance.
Yes, no, definitely. I think it ties in with Stephen's comment. If we can optimize the structure, it's a capital saving for the clients. But yes, I think especially vessel motion modeling has come a long way in just a few recent years. It's becoming more and more accurate and more accessible as well. So yeah, we've seen a lot of new applications, not just South Africa and Africa, but obviously around the world. But yeah, it's keeping another team busy as well. So it's definitely picking up.
Excellent. All right. Well, I've done quite a lot of talking myself. So if there are there any other questions from the floor? Yes, Nelson. Yeah.
Yeah, I wish my wide range of my colleagues were here. I think when all of you were just giving presentation about this toolkit, it sounds very, very, very extensive. I think these days, some of the challenges have to do with being able to make decisions within a very, very short time. If I make an example of a storm incident of 2017, I still remember in Durban, I still remember very, very well. In the news, it was just said, there's a storm in Port Shepstone. And then 2 hours, it was in Durban. No one said how intense is that storm. But when it hit Durban, it only took 2 hours for the whole of Durban to be standing still. And if we had the tools to predict real-time tools, probably Harbour Masters would have evacuated the vessels that were in the port. But we couldn't because I don't think our tools are at that level. And I think there's a lot of information that was presented today, and I hope you'll share the presentations with us. Personally, I really want to digest it to see what challenges we can take away with some of them. It's a wide range, and as an environmental scientist, I think about you see the amount of pollution that comes down some of our port to a point that they threaten a collapse of the entire ecosystem. We've actually never got to the point of modeling. We do sample, we do the analysis, we know the condition of the water, and it changes from time to time depending on the storm and the number of things that would have been coming down those catchments. I hope you'll share the presentations with us so that we digest. But thank you very much for this session. Thanks.
All right, excellent. Thanks, Nelson. Yeah, I think just a couple of comments from my sort of side of things is, yeah, I mean, from the forecasting elements, I mean, you do need to start with some of these model setups to be able to forecast various sort of events and stuff like that. And we are actually running some real-time applications with Gainy Water. There is some stuff that's integrated with City of Cape Town on their urban networks and stuff like that. So it is possible to set these things up. And yeah, I mean, the consequent savings that you can get from running these applications in real time are, yeah, I mean, they can be quite significant. But and then in terms of presentations, etc., we'll share what's available to you. So we will send that out, and we'll give that to anybody who's interested. And yeah, if you're wanting to include more colleagues into a specific presentation related to some specific component of the modeling softwares or one of the modeling packages, yeah, please reach out to us and we'll quite happily set something up that will enable that to happen. And yeah, but I think on that note, I'd like to thank everybody for their time. I'd like to especially thank the presenters. Very good presentations that were run through from dear Andrea with DHI, where he gave us a really comprehensive overview of the different modeling packages and applications, as well as some really cool examples. I liked some of that stuff with the Venice implementation. And then, yes, Stephen and Christian giving some really nice local examples of the application of the technology at a local level. So thank you very much, gentlemen. And also thank you for mainly sticking to your time. You did very well. And thanks everybody for attending. And yeah, any questions, please reach out to us and let us know, and we'll respond as quickly as we can. Thank you.
Thank you very much.
Thank you,
Thank
bye.
you, Jason. Thank you.
Thanks. Cheers.
Thank you. Bye.
Bye, everybody.
Thanks. Bye-bye.
Thank you,
Bye,
Brian.
everyone.
Yes, bye.